Alright, so this kind of question is a pretty common one, and we see this often with gravitational fields, electric fields, and magnetic, well, to a lesser extent magnetic fields actually, but we can do it with all three. So, pretty common problem, we have two different bodies here, so we've got a sphere A and a sphere B, and there's a line between them, and as soon as you see something like this, you should be thinking to yourself, right, okay, chances are this is going to be something about moving from towards one sphere and the other. And indeed it does say, okay, a charge plus q on A is larger than the charge plus little q on sphere B. And then a movable point P is located on the line joining the centres of the two spheres. The point P is a distance x from the centre of sphere A. Now, the student that sent me this question didn't include the mark scheme or the rest of the question, but my guess would be they'd probably go on to ask you what would be the distance x such that the work done on the potential is zero, or that the force in it was zero, because you can see later on in the question, you're going to be asked to sketch a graph to show the variation with x of the electric potential V between the centres of the two spheres. So when we do a question like this, what I always try to start with is just think about, just imagine what would happen. So just think about the forces on a particle or a test charge as we go from one to the other. So if I start at the surface of sphere A, well, clearly I've got a large field strength here. It's a charged object, so it's going to be repelled. So I'm going to see a force acting this way on it. Now, as I move and I go over towards sphere B, well, over here again, okay, B has a smaller charge, but it still does have a charge, and I'm much closer to B than I am to A. If we remember, the force due to electric field strength is the electric field strength, the charge on the sphere multiplied by our test charge over 4 pi epsilon naught r squared. So because that's an r squared term there, the fact that I'm so much closer to sphere B than I am to sphere A means that the charge of B, or the force of B, will dominate. I'm going to have a force acting that way. Now, what that should also tell you is that if I was to think of it in terms of, maybe if I do this as a graph, if I think of a graph of force against distance x, then what I would see is a large force when I'm at the surface of sphere A, and that force will reduce, and then it will actually change direction as I go towards sphere B. Now, I don't think the gradient of that is actually right. The gradient, if anything, is going to be a curve more like that, isn't it? Yeah, that's the kind of thing I'm going to get with my force graph. Because, as I say, I'm doing work against it. Now, this is where it gets a little bit trickier, because in this particular question, you were asked to sketch a graph to show the variation of electric potential V. So if we remember electric potential, that is the work done bringing a test charge from infinity, from an infinite distance, to a point. So again, let's just look at these two spheres. Now, if I was to zoom way out, what we would see is that they would act like a single point charge. So if you imagine me getting a test charge, and just bringing it from infinity towards these spheres, that's kind of what I'm being asked about. And as I go from infinity to these points, I'm going to be the whole time overcoming repulsion between these two spheres, because this one is always going to be repelling it, and so is this one. With one, so even if I go from, say, this point here, let's change colour so it's the obvious. If I'm at this point here, then I've got a force from A, or acting on it in that direction, and a force from B acting on it in that direction. So kind of the resultant force of those two will be that way. So there's no path I can take that wouldn't involve doing work. So I think it would be fair to say that I'm not going to have any negative areas here because it's always going to take me energy to push a positive charge towards it. So I can probably get rid of this. The second thing I can say is, well, let's look about on this line. I know that the electric potential inside a sphere is 0 because the field strength is 0. So it's going to look something like that. So now I've got to ask myself the question, okay, so what will my highest points in this graph be? So I'm expecting it to do something like this. I'm expecting a discontinuity where this is going to spike up sharply. And I'm going to also expect a sharp spike here. Now again, if I think about what I would feel if I pushed towards it, if I've got this test charge and I'm pushing it this way, I would expect to have to put work in. And there's going to be a minimum point around here somewhere, and I'm going to have to put work in again to get this way. So again, I think that the kind of shape I'd be looking for will be something like this. Now I also know that why isn't that working? I know that the charge on B is smaller, so actually I'd probably expect the peak here to be a little bit lower. So trying to erase this, but oh, there we go, there's my eraser. So I actually expect it to look something like that. Now I've just got a question in my mind, where will this minimum point be? And again, if I think about it this way, well, I know that the point P, actually I think it's probably drawn roughly to scale because the charge on this one is larger. So actually, no, sorry, it's not drawn to scale because I think I'd have to get closer to sphere B than sphere A in order to have those two forces cancel each other out. So that would give me this minimum point. So actually, I think just by chance, I've kind of drawn this minimum point at about the right, well, possibly the right distance. Obviously, we don't know how much bigger sphere A's charge is than sphere B. Can we put any numbers to this now? So let's say that when we are here, so I'm going to just change colour one more time to make it really obvious. So at this point, what will V be? So remember that electric potential, we get rid of the squared term. So electric potential is Q over 4 pi epsilon naught just R. Now, I've got two spheres, so I can add together the work done through both of them. So that will be plus little q over 4 pi epsilon naught. And I'm going to call this one, let's get rid of that R because I'm not dealing with R anymore. I'm dealing with X as my distance here. And here, this will be the distance from that one, so that will be, what would that be? Actually, it wouldn't be X, wouldn't it? Let's not call it X. At this one, it will be R, because I'm a distance 1 radius away. And on this one, it will be D minus R. Yeah, D minus R, won't it? Because this is distance R. So it'd be D minus 2R. Okay. Can I do anything else with that? Well, I suppose I could take out these common factors. So I could say V is 1 over 4 pi epsilon naught, lots of Q over R plus little q over D minus 2R. So I could mark that as a point here. And then on B, this point here, this would have a spike or a peak at where V is equal to 1 over 4 pi epsilon naught lots of, and this time it will be little q over r again, because that's the distance from the centre of the sphere. And then add in, this time it will be big Q over d minus 2r. So that will be where we'd meet the axis there. And if you're given numbers here, you could go and work those out. And then for this minimum point, that's going to occur at such a distance that the force on these two are equal. So we're going to get this point where the force due to sphere A is equal, but in the opposite direction to the charge, so the force due to sphere B. And that's quite a common question that you get asked a lot. You might just maybe with say orbital transitions, if you're going from Earth to the Moon, they might ask you what's the point at which the gravity of Earth, or the force of gravity due to Earth is equal to the force of gravity due to the Moon. So at this point, so I'm kind of dealing with this. Where is this distance here? So I can use the force equation here. I think I could probably use the potential equation as well, actually. But let's use the force equation because I know that the two are going to be equal. So I am saying that the force due to sphere A is equal to the force due to sphere B. Let's put in some numbers to that. So I can say that big Q over 4 pi epsilon naught, that is now going to be x. That will be equal to little q over 4 pi epsilon naught, and this one will be d minus x, because that is this distance here. Yes, that will be d minus x. Good. And I've got a common factor here, so I can just remove those. So I get q over x is equal to little q over d minus x. And I could go ahead and solve that if I've been given q's and d's and x's and things, but I don't think I'm going to bother with doing that because I don't have the numbers here. But that will tell me, I can use that to calculate where this minimum will be, and once I've done that I could also go ahead and calculate what the value would be as well. But obviously in this particular question I haven't been given the numbers, so this is about as far as I can go without plugging in numbers. But hopefully you'll see these techniques that you can use. Like I say, I think the really important thing with this kind of question is to just imagine yourself pushing a test charge towards this. If you do that, you can start to get a feel for what this graph should look like. And then once you've got a feel for what it should look like, you can then start to interrogate these different points on it and say, well, can I calculate any values for there? And then you should find that they're not too difficult questions. Provided, like I say, that you just get this initial idea of what's happening. A lot of it then will just follow through.